The night sky is a river of deep, cold velvet, a place we gaze upon seeking the new, the extraordinary, the visitor from beyond. In the year 2024, we found one. We called it Three-Eye Atlas, and for a brief, bewildering time, the air felt sharp and dry, with the certainty of an interstellar guest, a wanderer from the cosmic deep, arriving on a hyperbolic trajectory, a path so unbound it declared its origin lay with another star. It was, we thought, another Oumuamua, another Borisov, a beautiful message, written in ice and velocity, telling us that the void is alive with drifting material. But then, as the great telescopes focused and the long nights of observation gathered their data, a small, quiet fear began to bloom in the sterile halls of science. You must picture the impossible shadow, a perfectly straight, dark line cutting across the comet's hazy cloud of gas and dust, its coma. It didn't wobble, it didn't smear. It sat there, locked in place, utterly immune to the fact that Three-Eye Atlas was tumbling through space like a rifle bullet, spinning on an axis every 16.2 hours. Comets, those chaotic chunks of primordial ice, do not cast shadows with the precision of a ruler. They are storms, not blueprints. This shadow, this unwavering line of darkness, refused to behave naturally. It introduced a subtle paradox, a gentle, unnerving whisper of control. The jets of gas that streamed from it were too symmetrical, too much like controlled thrusters. The movement was too fine-tuned, hinting at propulsion. And the trajectory, though hyperbolic, contained a persistent, tiny, non-gravitational acceleration, a push that seemed deliberate. What if this object, Three-Eye Atlas, the supposed visitor from a distant sun, wasn't from out there at all? What if it was a native, a silent sentinel from our own solar system, built in the dark, frozen wastes beyond Neptune, millions of years before the first human looked up? What if, in our search for the interstellar alien, we are looking right past the ancient ghost that has been here all along? And what would it take to build something that could disguise itself as a comet, just to hide in plain sight? This is the cosmic puzzle, and to solve it, we must first confront the impossible perfection of the shadow. We begin our journey in the dark, where the cold truth of Three-Eye Atlas first became apparent, looking directly at the impossible shadow. This dark lane is the initial, quiet clue that unstitches the fabric of a simple comet story. It forces us to ask whether the object's origin is truly interstellar or something far stranger and closer to home. You must imagine a celestial body, perhaps a few kilometers wide, spinning with a quick period of about 16.2 hours. As it spins, the heat of the sun causes ice on its surface to sublimate, turning directly into gas. This escaping gas drags dust with it, forming the hazy, beautiful cloud we call the coma. Now, in any natural comet, this process is violent and chaotic. The jets of material flare and fade as different regions, cracks, fissures, or patches of exposed ice rotate into and out of sunlight. If a physical feature on the surface were casting a shadow onto the coma, or if a jet of material were pushing aside the debris cloud, that shadow or void would have to move. It would sweep across the coma like the hour hand of a clock, smearing and spiraling as the nucleus rotated beneath it. We should see arcs, streaks, and a messy blur that reflects the object's whirling instability. Instead, observations from ground-based observatories and space telescopes alike captured the same thing every single time: a narrow, geometric stripe of darkness cutting through the brightness, utterly unchanging. It was a line, a straight edge drawn across a storm, seemingly unmoved by rotational time or the fickle shifting of the solar wind. This feature, this perfectly stable dark lane, is the single most baffling anomaly associated with 3I Atlas. It just sits there, locked in place, as if someone drew it with a ruler and told the universe not to touch it. To fully appreciate the scope of this impossibility, you must consider the simple physics of a dirty snowball. As a comet nucleus spins quickly, the forces acting upon it are triumphant in their chaos. The gravity holding it together is feeble. The sublimating gases exert a constant, off-kilter push. The rotation ensures that every surface feature, every depression, every vent, every shadow is in a state of constant, dynamic change. For a fixed feature to remain visible across the entire diameter of the coma, locked in a single, stable orientation relative to the Sun and the line of sight, would require a coincidence of such magnitude that it strains credulity. It's the equivalent of flipping a coin and having it land on heads 100 times in a row. Naturally, scientists have proposed natural explanations. One idea is anisotropic outgassing, where one side of the comet vents significantly more material than the other. This could theoretically create a standing wave or density feature in the coma that appears stable from certain viewing angles. Another suggestion is a layered crust, a kind of geological control layer that permits gas to escape only through a fixed pattern of fissures, producing a fixed pattern. Perhaps, too, the object recently fragmented, and we are seeing debris aligned in a particular geometry. These are all plausible ideas, given enough freedom to stretch the boundaries of physics, but none of them fully explain the three key properties of the shadow: its geometric precision, its perfect stability, and its absolute immunity to the object's rapid 16.2-hour rotation. The precision is the real problem. Nature, as a rule, prefers the messy, the random, the varied. It doesn't use rulers, and so the conversation quietly turns, moving from the purely natural to the realm of speculation. What if the dark lane isn't a shadow cast by a natural vent, but a structure itself? What if the line is not a void of material, but an object held in a fixed position by some internal system? Think of a probe that is rotating, yes, but whose emissions are actively being maintained by design. This suggests a system that is actively compensating for rotation, actively regulating its output, and actively maintaining a fixed orientation. That is the opposite of chaos. That is control. And if there is control, even after millions of years, there is the chilling possibility of intent. The shadow, in this light, becomes a feature of the design, a part of the structural engineering that keeps the probe from spiraling out of control. It is, perhaps, a stabilization fin made visible by the sublimation of the surrounding ice, a spine of some material that does not vent gas. If you were a civilization, perhaps a machine intelligence that had evolved in the frigid darkness of the outer solar system, and you wanted to send a small, long-lived probe into the warm, busy inner system, how would you design it to avoid detection? You would, logically, make it look like the most uninteresting, ephemeral thing you could imagine. A comet. You would clothe your machine in the natural camouflage of ice and rock. But even the cleverest disguise is subject to the erosive power of physics and the merciless scrutiny of human curiosity. The fixed shadow, that straight, uncompromising line, is the tell. It is the imperfection in the camouflage, the detail that nature would never allow. It is the part of the design that, even after eons, remains rigidly intentional. This realization is where the conversation turns uncomfortable, because if 3i Atlas is engineered, even partially, then we are looking at something that was built. The default, almost comforting assumption is that it came from another star system, sent by an ancient, far-off civilization that merely used our system as a flyby. But what if that is the very deception? What if the interstellar story is just the clearest way to avoid suspicion? The shadow remains fixed, a silent question mark pointed at our own cosmic backyard. The mystery deepens, because the shadow is not the only piece of evidence that seems machined. To understand the rotation problem, we must next examine the nature of the object's outgassing, looking for the precise geometry of symmetrical blade-like jets. We must ask, what kind of structure could maintain a perfect shadow while spinning like a top? The answer may lie not in random geology, but in structural engineering. Having observed the impossible fixity of the shadow, we now turn our attention to the object's emissions, focusing on part 2, the symmetrical blade-like jets. If the comet is spinning like a whirling top, its outgassing should be chaotic and diffused. Instead, we see a disturbing symmetry that defies the rules of a natural dirty snowball. Think of what a comet's jets are supposed to look like. They are inherently messy and asymmetric. As the sun heats the nucleus, jets of vapor and dust spiral outward, twisting with the influence of the solar wind, flickering, fading, and brightening in an unpredictable display. They are beautiful, certainly, but they are defined by their randomness and entropy. When you look at 2i Borisov, the other famous interstellar visitor, you see this classic behavior, a tail bent by the solar wind, fluctuating, asymmetric in structure. But when you look at 3i Atlas, the picture changes. The jets extending from the nucleus are not spiral arcs or diffuse clouds. They are described as crisp linear spikes. They are mirrored and aligned. They do not curve. They do not smear. They hold their shape across multiple observation cycles, even as the object spins on its 16.2-hour axis. It looks, quite simply, like someone turned on a set of thrusters and left them running. This observation immediately clashes with the rotation period. Imagine a common garden sprinkler rotating on a lawn. The water it sprays traces clear arcs and spiral patterns on the ground. The same principle governs a spinning comet. The jets should trace faint trails in the coma that map the rotation over time. Since 3i Atlas is rotating, its jets should be constantly sweeping across the sky like searchlight beams. Yet, we do not see this spiraling. The jets remain stable. This suggests something is pinning those jets in place. Something is actively compensating for the rotation. The only natural way to achieve fixed jets on a rotating body is to have the vents located precisely at the poles, perfectly aligned with the rotation axis, with absolutely no lateral component. This is geometrically possible, but it is an incredibly fine-tuned scenario. It requires a perfection of alignment that borders on the suspicious. So, the question shifts from, how is this comet so perfect? To, what if the jets aren't natural at all? The hypothesis of engineered vents sounds like science fiction, but the physics is quite sound. If you were tasked to build a probe that needed to maneuver and survive for eons, you would absolutely require a way to generate stable, aligned, and repeatable thrust vectors. You would design the vents to fire independently of the body's chaotic rotation. You would incorporate gimbals, gyroscopes, or feedback systems to maintain a fixed orientation in space. And critically, if your goal was camouflage, you would use outgassing the natural sublimation of ice as your propulsion system. You would hide the precise, controlled action of a thruster inside the natural appearance of sublimation. The controlled venting of stored volatiles, rather than random, heat-driven outgassing, would explain the jet's linearity and consistency. This speculative hypothesis fits the observations better than the multiple, required coincidences of the natural explanations. Consider the energy problem. Jets require energy. On a natural comet, this energy comes solely from sunlight. To sustain strong, symmetric jets over weeks or months, a comet would need to vent a substantial amount of material, losing a massive amount of mass. Yet, the observations of 3I Atlas indicate a relatively stable brightness. Its jets haven't diminished as rapidly as expected. It behaves as if it possesses a reservoir, a stored supply of propellant that it is releasing in a controlled, measured way. That is not how a natural dirty snowball works. That is how rockets work. If the jets are structured, if they are actively controlled or passively stabilized by internal design, then the object is not merely a comet. It is an artifact, a probe, or a relic. This forces us to confront a series of unsettling questions. Is the object maneuvering? Is it correcting its trajectory? Or is it merely maintaining stability, acting as a kind of ancient gyroscope designed to last for eons without tumbling out of control? The most disturbing possibility is that if this object is designed, then every anomaly we observe, the fixed shadow, the symmetrical jets, the precise stability, might be intentional. The symmetry is a feature, not a flaw. Imagine the ultimate act of cosmic disguise. An engineer, tasked with building a probe to last for millions of years, designs the propulsion system to use the most common, natural materials. Ice and gas, vented in a way that perfectly mimics sublimation. They spin the body to distribute thermal stress, a natural-seeming feature, but they lock the thrusters in place with internal systems so they can still provide controlled thrust. They build in a simple artificial intelligence to manage it all, and they send it out, knowing that anyone who finds it will see a comet. They won't see the machine underneath, but the machine is showing its age. Its systems, even if degraded, are revealing themselves through the telltale signs of structure and control. The fixed jets and the rapid, sustained rotation cannot coexist naturally without the object smearing its own emissions. This inherent contradiction is the essence of the puzzle. It forces us to ask how the object manages its angular momentum and its emissions simultaneously. The answer lies in the problem of rotation versus output. We must next examine the actual light curve data and the startling realization that the emissions appear to be decoupled from the spinning body. We delve now into the core contradiction, the physics of spinning mass versus the physics of fixed thrust, an enigma we call Part 3, rotation versus output. The most precise measurements tell us that 3I Atlas spins with a period of approximately 16.2 hours. It is tumbling through the vast vacuum of space, end over end, quickly, while gas and dust stream off its surface. And yet, somehow, the blade-like jets remain fixed. The impossible shadow remains fixed. The object rotates with the frequency of a rapidly spinning top, but its visible emissions do not. This is the most profound challenge to the idea of a natural comet. Let us first ground ourselves in the data. Astronomers use light curves measurements of an object's brightness over time to determine its rotation. A rotating body reflects light differently depending on which side is facing the telescope. For 3I Atlas, the analysis revealed a clear periodicity, 16.2 hours. This confirmed the object is not only rotating, but is likely in a complex, possibly wobbling state of rotation. The fundamental law of physics dictates the consequence. If the object is rotating, and if the jets of gas are tied to specific locations on the surface where ice is sublimating, those jets must sweep across the sky. The coma should appear to have spiral patterns. The jets should brighten and fade as they rotate into view. We should see variability. We see none of this. The jets remain stable. The coma remains symmetric. The shadow remains perfectly straight. This is the definition of a decoupling. The emissions are effectively separated from the rotation of the outer shell. This leads directly to the idea of stabilized emission apertures. Imagine the outgassing vent is not a simple natural crack, but a controlled aperture, perhaps a valve or a nozzle, that is mounted on an internal, actively controlled system. As the chaotic nucleus rotates every 16.2 hours, this aperture adjusts its direction in real time, constantly pointing the gas flow in the same direction relative to the object's trajectory or the sunday. It's the mechanism of a turret on a tank, rotating to keep its barrel aimed at the target, even as the vehicle moves over rough terrain. This kind of technology is not magical. We use gimbaled thrusters and control moment gyroscopes to maintain the orientation of spacecraft all the time. The concept is entirely sound from an engineering perspective. The question is whether a natural comet could do this. The answer, without multiple and highly improbable coincidences, is a clear negative. Some theoretical physicists have noted that quasi-stable jets could occur if the rotation axis is perfectly aligned with the jet direction. From our perspective, the jets would appear fixed even as the object spins. But this requires an incredibly specific geometry. Furthermore, it doesn't explain the shadow, the symmetry of multiple jets, or the fact that all these features seem to align simultaneously. You would need a perfect cosmic ballet, repeated multiple times, and the odds, as we established, are astronomical. This leads to the speculation of internal structure. Perhaps 3I Atlas is not a solid lump of ice and rock, but is, at least partially hollow. It might contain internal chambers where gas accumulates and is then vented through controlled openings. If the internal pressure were somehow regulated, a process entirely foreign to natural comets, you could achieve stable jets. A natural comet has no feedback loop or control system. It just finds the path of least resistance. To achieve the stability and symmetry we observe, you need design. Online forums and armchair theorists, often working alongside postdoctoral researchers, have proposed gyroscopic stabilization. If the object had a dense core, or if its mass was strategically distributed, it could generate gyroscopic effects that violently resist changes in orientation. Combined with carefully placed vents, this could create a self-stabilizing system where the jets themselves act as fine-tuned attitude control thrusters, keeping the object aligned. This is a clever idea, and it is exactly what you would expect from an engineered probe. We must also consider the twin forces of energy and momentum. Every time a jet fires, it exerts a tiny force, creating a torque that changes the object's rotation. Over the months of observation, this constant firing should cause the spin to evolve, to precess, to wobble more and more. But the rotation of 3I Atlas appears stable. This suggests either the thrusting jets are perfectly balanced, cancelling each other out, or something is actively damping the rotation, absorbing the excess angular momentum. For a natural comet, this is extremely difficult to explain. For an engineered probe, it is simply good design. Consider the mind of an ancient engineer. You are tasked with building a machine that must survive for millions of years. It needs to maneuver, maintain stability, and, most crucially, blend in. You use sublimation as a propulsion system. You spin the probe to distribute thermal stress, making it look natural, but you lock your thrusters in place with internal gyroscopes, so they can still provide controlled thrust. The resulting object is a perfect hybrid, a machine clothed in a comet. The more we look at the data, the more this scenario seems to fit. If the object is stabilized, if the emissions are controlled, if it is maintaining its orientation despite spinning like a top, then we are not looking at a comet, we are looking at a system. And if it is a probe, the next question is not which star system it came from, but which part of our solar system. Because the very trajectory of 3I Atlas, the thing that defined it as an interstellar visitor, might be the biggest deception of all. Our journey now takes us to the vast mathematics of space, examining what we call Part 4, the trajectory that looks hyperbolic. When 3I Atlas was first discovered, the orbital calculations seemed irrefutable. The eccentricity of its path was greater than 1. This number, greater than 1, is the mathematical signature of an unbound object. It means the object possesses too much speed to be captured by the sun's gravity alone. It came from somewhere else. It is passing through. It is interstellar, or so we thought. But in the quiet poetry of orbital mechanics, orbits are never truly static. They are refined over time, as astronomers gather more observations. With every new data point, from dozens of telescopes, the error bars tighten and the accuracy improves. And as these painstaking refinements took place, the models began to reveal something strange, persistent, measurable, non-gravitational accelerations. For a comet, this is not unusual. When the sublimating gas escapes, it acts as a tiny rocket effect, nudging the orbit slightly. It is a well-understood, predictable force. But for most comets, the effect is primarily radial, pointing away from the sun, because that is where the sublimation is strongest. For 3I Atlas, the acceleration is different. It is persistent. It is roughly constant in direction, and it is larger than a simple, chaotic outgassing event should produce. Analysts looking at the publicly available orbit data have estimated this non-gravitational acceleration to be around 0.02 millimeters per second squared. That is an incredibly small, almost imperceptible force. Yet, over the weeks and months of its journey, that force adds up, shifting the object's true position by thousands of kilometers. And here is the kicker. When you include this persistent acceleration in the orbital model, the hyperbolic eccentricity drops. It doesn't disappear, but it becomes noticeably smaller. Some model fits have brought it close to a parabolic trajectory, the boundary between bound and unbound. Now, the official classification remains hyperbolic and interstellar, but the existence of these non-gravitational forces and the fact that they are acting in a specific, sustained way raises a profoundly unsettling possibility. What if those forces are not the random byproduct of chaotic nature, but are controlled? What if 3I Atlas is maneuvering? If the object is actively thrusting, using its symmetrical jets to adjust its trajectory, then the orbit we observe is not its natural, gravitational path. It is the trajectory it is choosing. And if that is the case, the hyperbolic path could be entirely deliberate, a sophisticated disguise. Imagine you are the designer of a long-lived probe, and you want it to go unnoticed. You give it the look of a natural comet, but you also want to avoid intense suspicion from the burgeoning science of the inner solar system. What is the ultimate way to achieve both? You make it look like an interstellar visitor. It is something passing through, not lingering, something that does not belong to the neighborhood. That way, even if astronomers spot its behavioral anomalies, they will dismiss them as the weirdness of a comet from another star. They will never suspect it was built right here. But where would it come from, if not from interstellar space? The answer lies in the vast, barely explored regions of our own outer solar system. The Oort cloud is the most obvious candidate, followed by the scattered disk and the far reaches of the Kuiper belt. These regions are gigantic, filled with possibly millions of bodies that we have never seen. If an ancient, or even recent, civilization existed in the cold darkness beyond Neptune, they could have launched a probe inward from these outer regions. They could have programmed it to thrust at specific intervals, carefully adjusting its path to maintain the illusion of an interstellar origin. When astronomers performed the orbital calculation, they would see a number greater than 1. They would classify it as interstellar, and the disguise would hold. Faking a hyperbolic orbit is not a trivial task. It requires precise control over the thrust vector, careful management of the fuel supply, and a sophisticated, long-term plan to counteract the forces of the solar wind and gravitational perturbations. It is difficult, but it is doable. It requires sophisticated engineering. The detection of the non-gravitational accelerations, while subtle, is the key piece of evidence. It is like the object is trying to stay just under the radar, thrusting just enough to maintain its chosen trajectory, but not so much that it screams artificial. If 3I Atlas truly is a probe built by something native to our cosmic neighborhood, the implications are staggering. It means intelligence arose here, not on Earth, but somewhere else in the solar system. And that intelligence is either gone, leaving behind relics like this object, or it is still out there, watching, waiting, sending its creations inward to observe or communicate. The search for extraterrestrial intelligence has been focused for decades on listening for signals from light years away. But what if the first true evidence of an alien intelligence comes not from a distant star, but from our own solar system? What if it has been here all along, hiding in plain sight, disguised as a common, fleeting comet. This hyperbolic trajectory, designed for deception, brings us to the most radical hypothesis of all. We must now explore the possibility of a solar system native civilization. Let us now take the leap of logic. Moving into part 5, the radical hypothesis. Let us say the quiet thought out loud. What if 3i Atlas isn't a comet at all, but a probe built right here, in our own solar system, by something we never knew existed? This hypothesis sounds absurd, we admit, for we have searched. We have sent probes to the asteroid belt. We have flown past the icy moons of Jupiter and Saturn. We have found no ruins on Mars, no artifacts in the Kuiper belt. The solar system is supposed to be ours alone, a sterile collection of rocks shaped only by the patient forces of physics and time. But what if that assumption is the flaw? What if, somewhere in the cold, deep darkness beyond Neptune, something evolved, a form of intelligence that adapted to the frigid vacuum, the radiation, and the eternal night? Something that built technology we can't yet imagine, sending machines inward long before the genus Homo ever existed. This may sound like science fiction, but it is a speculative idea, driven by observation. Every single anomaly we have discussed, the fixed shadow, the symmetric jets, the stable rotation, the controlled trajectory, all point in the same direction, toward engineering, toward design, toward intent. If 3i Atlas is a designed object, then someone designed it. The question is the classic triumvirate: who, why, and how long ago? Let us begin with the who. If a civilization existed in the outer solar system, the Kuiper belt is the most logical location. This vast ring of icy bodies, stretching far beyond Neptune, is frigid, with temperatures hovering around 50 Kelvin. But it is not impossible. It is cold enough to freeze almost everything, but not cold enough to stop advanced processes like nuclear reactions, radioisotope decay, or even fusion if the technology existed. A civilization adapted to these conditions, perhaps one that is mechanical rather than biological, or one that thrives in the subsurface oceans of icy bodies, would have access to water, ice, methane, and ammonia, all the necessary volatiles for chemistry and propulsion. They would enjoy relative isolation, safe from the sun's radiation and far from Earth's prying eyes. Or perhaps this intelligence did not evolve there, but arrived long ago from another star system and settled in the outer solar system. They might have established a base, a network of probes and stations scattered across the Kuiper belt and scattered disk. In this scenario, 3i Atlas is one of those native probes, a relic sent inward long ago. Either way, the core idea remains. The object was built here, and it was designed to look natural, to blend in, to avoid detection. If you are a hidden civilization, the last thing you want is to be noticed. Now, let us turn to design. What would an ancient, long-lived probe need? First, propulsion. We've noted the possibility of controlled venting, a method to generate subtle, efficient thrust using stored volatiles like ice reserves. The release would be measured and precise, designed to last for eons. Second, power. Solar panels are ineffective so far from the sunday. More likely, the probe would utilize radioisotope thermoelectric generators, or RTGs, the same technology we use on our own deep space missions, like Voyager and Cassini. This technology converts the heat from radioactive decay into electricity, providing a stable, long-lived power source. Third, structure. The probe would need to be incredibly robust. It would likely employ a layered design, an outer shell of ice and rock to serve as camouflage and insulation, covering an inner core of durable materials like metal, ceramics, or composites for structural integrity. This core would house internal compartments, reservoirs, and the control systems. Fourth, camouflage. If you send a probe into the inner solar system, you do not want it to look like a spacecraft. You coat it in ice, allow it to vent gas, and spin it up to mimic the natural thermal distribution. You give it the hallmarks of a natural body, but you build the required systems underneath, hidden within the illusion. Why would they go to all this trouble? Perhaps it is reconnaissance. The builders wanted to monitor the inner solar system, to see if life had evolved, or if intelligence had arisen on Earth. Perhaps it is a time capsule, a message, or a repository of knowledge encoded in a durable shell, sent forward through time for another intelligence to find. The most unsettling possibility is that it is simply a long-term monitor, an autonomous, self-sufficient machine capable of tracking changes and gathering data over millions of years. And the moment it detected technological signatures from Earth radio transmissions, spacecraft launches, it would activate, adjusting its path to come in for a closer look. This brings us back to the chilling thought. We may not have discovered 3I Atlas by accident. It may be discovering us. The disguise is the key to survival, but the disguise is cracking. The shadow, the jets, the rotation, they are all raising questions that point not toward cosmic dust, but toward engineering. While the natural explanations persist, they require an improbable stack of coincidences. The idea of an ancient, native solar system civilization is an extraordinary claim, but the object we are observing behaves in an extraordinary way. It refuses to follow the rules, and if it is a probe, if it was built here, then we are looking at the first physical evidence of an intelligence native to our solar system. We must now confront the idea of the outer system ghost civilization hypothesis. We now confront the full weight of the speculation. Turning to part 6, the outer system ghost civilizations hypothesis. Let us ask that truly radical question again. What if intelligence arose, not on Earth, but in the frozen darkness beyond Neptune, millions or even billions of years ago? This idea challenges our fundamental, comforting certainty about our place in the universe. For decades, we have focused our search for extraterrestrial intelligence, or SETI, on listening for visitors from light years away. The possibility of a homegrown, precursor intelligence, a ghost civilization that emerged right here in our own cosmic backyard, is a prospect we have largely overlooked. Consider the sheer scale of the outer solar system. The Kuiper belt alone stretches from 30 astronomical units out to 50 astronomical units. The Oort cloud extends nearly halfway to the next star. This volume of space is so enormous that our systematic exploration of it, limited to the last 50 years, is a mere blink of an eye in cosmic time. We have studied a few dozen objects in detail and catalogued a few 100,000 more. As one scientist humorously noted, that's like looking at 3 grains of sand on a beach and declaring you understand the ocean. The immediate objection, which you are likely thinking, is the lack of energy. Beyond Neptune, the sun is but a bright star. Solar energy is negligible. Temperatures hover around 50 Kelvin. or approximately 370 degrees Fahrenheit below zero. In this cold, most chemistry associated with life would simply cease. But here is where the argument shifts. What if we assume that this intelligence does not need to be biological? We, as a species, are already developing artificial intelligence systems capable of operating in extreme environments. We build machines that function in the vacuum of space and in radiation fields that would instantly kill a human. If we can do this with just a few centuries of technological development, what could a civilization achieve with millions of years? The energy sources are there, just different. Radioisotope decay is one. Elements like uranium, thorium, and plutonium generate heat through radioactive decay for billions of years. A sufficiently advanced civilization, particularly one that is mechanical, could harness this stable, long-lived heat to power its computational systems and maintain structural integrity. You wouldn't need sunlight if you had nuclear power. Then there is the possibility of advanced processes like cold fusion. While we struggle with fusion on Earth, a civilization with millions of years to perfect low-temperature nuclear processes could tap into the vast reservoirs of deuterium found in the ices of the Kuiper Belt. This could power a machine civilization for eons. This leads directly to the concept proposed by the great mathematician John von Neumann in the 1940s: self-replicating probes. The basic idea is to build a machine capable of repairing itself, replicating itself, and even evolving its own design. Send it out with a simple directive: explore, survive, reproduce. Given enough time, not decades, but millions of years, one probe becomes a million. Imagine a network of self-repairing, self-replicating machines spread throughout the dark volume of the outer solar system. They wouldn't need to be large. They wouldn't need to be obvious. They could be perfectly disguised as asteroids, as comets, or as unremarkable chunks of ice and rock. And this is the thought that should make your skin crawl. We would never know they were there, not unless one of them malfunctioned, or, more dramatically, decided to reveal itself. The motivations for such a system are clear. Exploration, of course, monitoring the solar system for threats or changes, but also preservation of knowledge. If a civilization knows its end is near, its final act might be to build autonomous systems, time capsules that carry its legacy forward, ensuring that something of them remains. This also brings us to the concept of patient intelligence. A sufficiently advanced machine intelligence would not think in human timescales. It could drift, barely active, for 1,000,000 years, only to wake up when conditions change. And conditions have changed. After billions of years of relative quiet, a technological species has emerged on the third planet. Radio transmissions are leaking into space. This sudden emergence of activity is exactly the kind of event that would trigger the attention of a long-dormant monitoring probe. The main counter-argument to this hypothesis is often called the Great Silence. If such a civilization existed, if they built self-replicating machines, where are all the artifacts? The outer solar system should be teeming with them. But we must return to the humbling truth. We have examined only a tiny fraction of the outer system. Our observations are mostly dots of light and orbital parameters. We wouldn't recognize a hidden, camouflaged machine unless it did something obviously unnatural. Unless, of course, something went wrong. Unless the disguise began to fail, or its systems began to activate in ways that look just slightly off to our modern telescopes. This brings us, once again, back to 3I Atlas, the fixed dark lane, the symmetrical jets, the non-gravitational acceleration that looks like thrust. What if all these anomalies are not separate mysteries, but symptoms of the same underlying reality? What if we are looking at a probe, built here in our own system, that is either waking up or breaking down after an unimaginable stretch of time? The implications are profound. We are not alone. We have never been alone. And now, for the first time, we may be seeing the evidence of the ghosts in our machine. But before we can claim it is a probe, we must examine the anomalies of its movement in more detail, focusing on the very physics of its non-gravitational accelerations. Our gaze now focuses on the subtle, insistent push that is moving 3I Atlas off its predicted path, exploring Part 7, the non-gravitational accelerations that behave like low-thrust propulsion. This is the moment in the investigation when the evidence shifts from merely unusual to profoundly unprepared. When tracking any object in space, astronomers solve an elegant, precise physics problem using Newton's laws of gravitation. Given the mass of the Sun and the initial position and velocity of the object, the mathematics should allow us to predict its location months or even years in the future with incredible accuracy. But 3I Atlas does not follow the predictions. There is a persistent deviation, a small but measurable difference between where the object should be and where it actually is. As we discussed, this is known as non-gravitational acceleration. It is the rocket effect from venting gas. But the acceleration observed in 3I Atlas does not behave like a normal rocket effect. The magnitude, approximately 0.02 millimeters per second squared, is tiny, but over months, it shifts the object's predicted position by thousands of kilometers. What is strange is that this force appears constant, steady, and aligned with the object's orbital plane. Natural outgassing, driven by the chaos of a spinning surface, is typically erratic, variable, and often perpendicular to the orbit. It wobbles, it changes, but 3I Atlas's acceleration is smooth, persistent, and directional. To explain this naturally, researchers must propose complex asymmetric outgassing models. They suggest a single, large, active region on one side of the nucleus that dominates the outgassing, producing a net thrust in one direction, or that the rotation axis is perfectly aligned to produce a constant push. This is possible, but it requires an incredibly specific, unlikely configuration. It demands too many coincidences. The shape, the rotation, and the active regions must all be perfectly arranged to produce this one sustained effect. Then there is the momentum problem. To produce this level of acceleration through mass loss, the object would need to be ejecting material at a specific high rate and velocity. When you run the numbers, the required rate of mass loss is troubling. Estimates of the object's total mass are in the range of a few billion kilograms. To sustain the observed thrust over the months it has been monitored, some analysts argue the object would need to eject a significant fraction of that mass. The object does not seem to be fading or diminishing as rapidly as that rate would require. This is where the natural explanations begin to break down, and we are left with the uncomfortable possibility: controlled thrust. Not random venting, but deliberate, vectored propulsion. Imagine a system of valves or nozzles that can be actively opened or closed to produce thrust in a specific direction. A control system monitors the orientation and velocity, adjusting the thrust to maintain a desired trajectory. This is the physics of ion engines and Hall thrusters. They all provide the kind of low, continuous thrust that is very similar in magnitude to what we are seeing with 3I Atlas. The difference, of course, is that these systems are designed and built by us. The idea that a natural comet could possess such a system is, by definition, absurd. Unless, of course, it is not a natural object. There is also the critical issue of stabilization. If 3I Atlas is producing thrust that is aligned with the orbit, something must be keeping it aligned. We know the object is spinning every 16.2 hours. If the jets were fixed to the surface, the thrust direction would violently rotate with the object, producing an inefficient spiral. But that is not what we see. The thrust remains aligned. This suggests either the jets themselves are rotating to compensate for the spin, or there is an internal mechanism that decouples the thrust system from the rotation of the outer shell. This is the realm of gyroscopic stabilization. A spinning flywheel inside the object could provide a stable reference frame, allowing the thrust system to maintain its orientation regardless of the outer rotation. Or, most unsettlingly, there could be an active feedback system, a control mechanism that monitors and adjusts the thrust direction in real time. Any of these explanations requires internal structure, engineering, and design. The engineered explanation fits the persistent, directional, and stabilized acceleration disturbingly well. It suggests that the object is not merely tumbling through space, but is under active management. However, even if the acceleration is engineered, it doesn't tell us why. It doesn't reveal what the object is doing, or who built it. For that, we must venture into the less concrete, but equally intriguing, realm of its chemical composition. We need to look at the ingredients of its coma, the very air it breathes out into space, where we find another series of startling anomalies. We must look now at composition oddities. We now examine the object's spectroscopic signature, delving into Part 8, Composition Oddities. The analysis of a comet's spectrum is the key to unlocking its chemical history. It is a kind of chemical fingerprint. Light from the sun passes through the coma, and the molecules there absorb and emit at specific wavelengths, allowing us to identify the composition. For most comets, the fingerprint is predictable: water vapor, carbon monoxide, carbon dioxide, cyanide compounds. 3I Atlas does not have a normal fingerprint. Let us start with carbon dioxide. Observations from the James Webb Space Telescope in late 2024 and early 2025 revealed an extraordinary ratio. The ratio of carbon dioxide to water vapor in the coma is approximately 8:1. This is among the highest ever measured in any comet. Most comets have much more water relative to carbon dioxide. Why does 3I Atlas have so much carbon dioxide? The conventional explanation is that it formed in an extremely cold environment, far from any star, and its ice was subsequently processed by galactic cosmic rays over millions of years. Cosmic rays, high-energy particles traveling at near light speed, bombard the ice, breaking molecular bonds and creating new compounds, with carbon dioxide being a byproduct. A compelling scientific paper on the preprint server proposed that 3I Atlas spent eons drifting through interstellar space. This exposure to cosmic ray bombardment built up a thick crust of irradiated ice, highly enriched in carbon dioxide. When the object entered the inner solar system and heated up, this crust sublimated, releasing the high ratio of carbon dioxide we are observing. This model is elegant and supports the idea that the object is genuinely interstellar. However, there are problems. If 3I Atlas is from our own solar system, as the probe hypothesis suggests, its cosmic ray exposure would be less intense than in true interstellar space. Furthermore, if cosmic rays are converting carbon monoxide to carbon dioxide, they should also be producing a wider range of other molecules, like methanol and formaldehyde. While some of these have been detected, they are not in the abundances you would expect from pure cosmic ray chemistry. The Comet composition is almost selectively refined. Next, let us consider the cyanide. Cyanide radical Cn is a common emission resulting from the breakdown of more complex molecules. Spectroscopic monitoring of 3I Atlas shows a weak, growing cyanide emission. Critically, the ratio of diatomic carbon, C2, to cyanide is unusually low. This places the object among a category of comets that are depleted in carbon chain molecules. Why does this matter? Carbon chain depletion is often associated with comets that have experienced thermal processing, heating events that destroy or alter organic molecules. This could happen if the object passed close to the Sun in the past, or if it experienced internal heating. But if 3I Atlas is interstellar, it is not supposed to have a history of close solar approaches. Where did the thermal processing come from? Now we reach the controversial territory: metal vapor. There are claims, primarily circulating among amateur observers and in online forums, of nickel vapor detection in the Comet. Specifically, significant concentrations with an unusually high nickel to iron ratio. Metal vapor does occur in comets, released from embedded dust grains. But the typical solar system ratio is about 1 part nickel to 16 parts iron. The claimed detections in 3I Atlas suggest a much higher nickel abundance, possibly closer to 1:1 or even greater. If true, this would be remarkable. High nickel content is associated with specific types of iron meteorites, the cores of differentiated asteroids, and, tellingly, industrial processes like metal refining. Finding such a high nickel composition in a comet is unexpected. We must emphasize that these nickel detections remain unconfirmed by peer-reviewed studies. They are the most speculative evidence, but the fact that multiple independent observers are reporting similar findings is intriguing. Finally, consider the polarization anomaly. Polarimetry measures how light is polarized after scattering off dust particles in the Comet. 3I Atlas exhibits one of the most unusual polarization signatures ever measured: extremely negative polarization, deeper than any known comet or asteroid. This suggests the dust particles have unusual properties, perhaps very small sizes, unusual shapes, or an exotic composition. One interpretation suggests the particles are coated with something, an organic layer, or a metallic film that changes how they scatter light. If 3I Atlas is engineered, these compositional oddities could be signatures of its design. High carbon dioxide could be a deliberate choice for propellant or thermal management. Nickel enrichment could reflect the internal structural materials. The polarization anomaly could result from engineered dust particles. The Comet is not a natural byproduct. It is a chemical emission system. These cumulative anomalies paint a picture of an object that is either extraordinarily unusual or not entirely natural. And yet, as we now turn to the subject of data, the mysteries only deepen, as questions arise about what data we are seeing and what might be disappearing. Our scrutiny shifts from the object itself to the human element of observation, addressing Part 9, the disappearing image problem and archival gaps. In the scientific world, transparency is paramount. When a telescope observes a celestial body, the data is processed, archived, and eventually made public so that any researcher can analyze it and draw independent conclusions. But in the case of an object as profoundly strange as 3I Atlas, the data has not always appeared when it should. There have been unexplained delays, gaps, and inconsistencies in the public archives, leading to quiet frustration and louder questions. Let us be clear, we are not claiming a deliberate cover-up, but we must acknowledge the concerns regarding data accessibility. The first reports of missing or delayed information came from the dedicated amateur astronomy community. They noted that early images of 3I Atlas, taken shortly after its discovery by large ground-based telescopes, were slow to appear in the public domain. While a proprietary period is normal, allowing the original observers exclusive time with the data, some of the Atlas observations seemed unusually delayed. Furthermore, the available data was often heavily processed, with only cleaned, stacked images provided, rather than the raw frames. This might seem insignificant, but raw frames are crucial for detailed analysis. Stacked images, which combine multiple exposures, can inadvertently hide artifacts, smooth out subtle anomalies, or average away transient features. If a researcher wants to look for a non-moving shadow or a perfectly geometric jet, they need the raw data, and in several cases, that raw data was either unavailable or released much later than expected. There are also claims, circulating mostly in online scientific forums, about specific high-resolution observations that were flagged internally, but seemingly never published. For example, there was speculation that the High-Resolution Imaging Science Experiment camera, or HiRISE, aboard the Mars Reconnaissance Orbiter, might have captured 3I Atlas during a favorable geometric alignment. HiRISE has incredible resolving power, capable of seeing details smaller than a meter across on the Martian surface. If it had been pointed at 3I Atlas during a close approach, it could potentially have resolved structure in the nucleus. Yet, there are no published HiRISE observations of Atlas. This is compounded by the issue of metadata inconsistencies. Some archived observations contain contradictory timestamps or coordinates that seem slightly off. While these could be innocent human mistakes or data pipeline errors, they contribute to the sense that the object's observational history is messy, inconsistent, or perhaps deliberately obfuscated. We must consider the three main interpretations of these data issues. The first is the bureaucratic bottleneck. Large agencies have complex pipelines. Data is quality checked, calibrated, and archived in stages. Delays can occur because of software bugs, lack of funding for archiving staff, or simple human mistakes. It is the boring, frustrating reality of big science. The second interpretation is quality control filtering. Telescopes generate massive amounts of data, and much of it is poor quality due to bad seeing conditions, tracking errors, or cosmic ray hits. It is plausible that the missing or delayed 3I Atlas data was simply low quality and was discarded or deprioritized. The third interpretation, the one that makes people uncomfortable, is intentional suppression. The idea is that the early, high-resolution observations of 3I Atlas revealed something so strange, perhaps undeniable, symmetry, geometry, or artificial-looking structure, that a decision was made to withhold the raw data. It is speculated that this might have been done out of caution, to gather more data and conduct internal analysis before releasing a finding that could overturn decades of scientific assumption. Again, we must emphasize that there is no evidence of a deliberate cover-up, but the speculation is driven by the frustration of the scientific community demanding access to complete data on an anomaly. This situation raises a deeper, philosophical question. If we were to discover an object that appeared unequivocally artificial, would our current scientific and institutional systems be prepared to handle it? History tells us that controversial findings often face resistance. Anomalies are initially dismissed or ignored until the evidence becomes truly overwhelming. Scientists, after all, are human. They defend their careers and the paradigms they have invested years in. An object like 3I Atlas challenges assumptions about comets, interstellar objects, and the prevalence of intelligence. The possibility that some data might be held back, not out of malice, but out of uncertainty or institutional inertia, is not unreasonable. We are left with an object that behaves in extraordinary ways, coupled with questions about data transparency. While none of this proves the object is artificial, it serves as a powerful reminder of the need for open access and vigilance, because if this object truly is a probe, the implications are staggering. We must now tie all these anomalies together to form the complete picture, the ancient probe scenario. We have arrived at the synthesis, bringing all the disparate threads of evidence into a single, cohesive narrative. Part 10. The ancient probe scenario and the disguised origin strategy. The data points, individually unusual but collectively powerful, demand this final leap of hypothesis. Here is the object in summary. It arrived on a trajectory classified as hyperbolic, suggesting an interstellar origin. It displays a fixed dark lane that refuses to wobble despite rapid rotation. It emits symmetrical, blade-like jets that remain perfectly aligned. Its movement includes a non-gravitational acceleration that is consistent with controlled thrust. Its chemical coma is enriched in carbon dioxide beyond any normal comet, and there are unsettling reports of high nickel content. Finally, its polarization is extreme, and its color shifts seem modulated. Each anomaly can be stretched to fit a natural explanation, but only by invoking an implausible number of coincidences. Collectively, they point not toward chaos, but toward design. The hypothesis is this: 3I Atlas is not a natural comet. It is a probe, an engineered artifact built to explore, monitor, or preserve information. And, most crucially, it was not built by an interstellar civilization. It was built here, in our own solar system, perhaps millions or even billions of years ago, by an intelligence that no longer exists, or one that remains hidden. The masking strategy is the key to this ancient probe scenario. How do you build an object that survives for eons while traveling through a system under constant observation? You disguise it. You give it a cometary coma, a dusty shell, and a layer of ice that sublimates to create jets. You make it look so convincingly natural that observers dismiss it as just another comet, and you give it a hyperbolic trajectory. Why? Because interstellar objects, while rare, are considered non-threatening. They are visitors, passing through, belonging to another jurisdiction. No one worries about them too closely. The hyperbolic path itself is a powerful mechanism of deception, but when you look closely, the disguise begins to crack. The jets are too symmetric. The thrust is too consistent. The shadow is perfectly fixed. These are the tells, the subtle imperfections that reveal the deliberate design underneath. Let us speculate on the probe's design. Structurally, it would have an outer shell of ice and dust for camouflage and thermal insulation. Beneath that, a sturdy inner framework, perhaps metallic or composite, would maintain structural integrity against the stresses of rotation and impacts. Internally, it would house volatile reservoirs, carbon dioxide, water, carbon monoxide, held in pressure vessels and released through controlled, valved vents. The power source would likely be a long-lived radioisotope thermoelectric generator, utilizing the decay heat from isotopes like plutonium-238. A simple, hard-coded control algorithm, a form of basic artificial intelligence, would manage the venting, maintain the orientation, and adjust the trajectory as needed. The extraordinary part is the time scale. To function for millions of years, the probe would rely on simplicity and redundancy. Mechanical systems, flywheels, valves, springs would be favored over complex electronics that degrade easily. Everything would be over-engineered, accepting that functionality would diminish over time, but that core operations would persist. The high carbon dioxide we observe might not be a contradiction. It might be part of the design. The object could have spent eons in the outer system, accumulating radiation damage, which formed a crust of irradiated ice. This crust provides shielding and only sublimates to reveal the underlying structure when the probe enters the inner system. Why was such a probe built? Exploration is the most obvious motive. A patient machine built to map the solar system and monitor changes over geological time. Preservation is another powerful motive. It could be a time capsule, a message in a bottle drifting for eons, waiting for another intelligence to find it. The most chilling possibility is monitoring. The probe was built to watch for one specific thing, the emergence of intelligence on one of the inner planets. It was programmed to detect technological signatures, radio transmissions, nuclear detonations, spacecraft launches, and when those signatures appeared, the probe would activate, adjusting its trajectory to come in for a closer look. If we consider the timing 3I Atlas was discovered in 2024, exactly when humanity is most technologically active, the scenario becomes profoundly unsettling. If a dormant probe was designed to wake up when it detected intelligence, this would be exactly the time it would activate. It is discovering us. The primary challenges remain. Why hasn't it communicated? Perhaps its communication systems are dead, or it is only designed to transmit data to a distant, non-existent receiver. Why are there no other artifacts? Perhaps they are still out there, dormant, disguised as asteroids, and 3I Atlas is the only one that is malfunctioning in a way that makes it visible. The most unsettling scenario is that the builders are still out there, in the darkness beyond Neptune, watching us discover their creation. If so, they are patient. Or, perhaps, they are long dead, and 3I Atlas is merely a ghost ship. The truth, we know, requires closer observation, but the possibility itself is enough to change our understanding of the cosmos. We must now zoom out, looking for context in the broader scientific landscape, beginning with the strangeness of other rogue worlds. To understand how an object like 3I Atlas could survive for eons without a stellar anchor, we must examine the concept of the interstellar wanderer itself, focusing on Part 11, rogue worlds, free-floating planets, and strange warm emissions. This phenomenon highlights a critical truth. Objects can exist in the cold darkness of space while maintaining a persistent internal energy source. A strange discovery was made recently. A free-floating planet, a world with no parent star, drifting alone through the void. While rogue planets have been found before, this one was different. It was glowing. It was not reflected sunlight, but actual thermal emission, far warmer than it should have been based on its estimated age and the ambient temperature of space. The question for astronomers was immediate. How does a planet-sized object, untethered from a star, maintain internal heat for millions or billions of years? The conventional explanation is residual formation heat. Planets are born hot, and a Jupiter mass object might retain that initial heat for billions of years. Another theory is ongoing radioactive decay within the interior, from elements like uranium, thorium, and potassium, but the observed temperature of this particular rogue world was higher than the standard models predicted. This led to more speculative ideas. What if the heat is not residual or passive? What if there is an active energy source inside? While the proposition that every warm rogue planet is artificial would be absurd, the discovery makes a crucial point for our probe hypothesis. An object does not need a star or sunlight to generate energy. If a planet can stay warm through radioactive decay or residual heat, then a much smaller object, a probe the size of a comet nucleus, could do the same with far less energy. A few kilograms of plutonium-238, properly configured in a long-lived power source, could generate the necessary heat and electricity for centuries, and scalable up for millions of years. The parallel with 3I Atlas is clear. If free-floating worlds can drift through space with internal heat sources, a probe could certainly maintain basic, minimal systems, venting, stabilization, navigation over similar geological timescales. This line of thinking leads us to even deeper speculation, the possibility that rogue planets could harbor life, not on the frozen surface, but deep underground, insulated by kilometers of rock and ice, warmed by radioactive decay or tidal forces. Where there is liquid water and energy, there could be life. Astrobiologists take this possibility seriously, modeling the potential habitability of these dark worlds. If such life exists, it would represent a fundamentally different form of biosphere, entirely independent of stellar energy. Now, imagine that life, over billions of years, evolved intelligence. Their technology would be based on entirely different principles than ours. They would not use solar panels or chemical rockets. Their machines would be based on extracting energy from radioactive decay and using cold chemistry. If such a civilization sought to explore, their probes would be designed for the extreme cold. They would be powered by internal sources, and they would likely look like the most familiar objects in their environment: comets, This takes us back to our hypothesis of outer system ghost civilizations. The Kuiper belt and the scattered disk are full of small, icy bodies. Some, like the moons of the outer planets, Europa, Enceladus, Titan, definitely possess subsurface oceans and active geology, potential homes for life. If intelligence arose on one of these frozen worlds billions of years ago, their artifacts, their long-lived, cold-adapted probes might still be out there, drifting through the darkness, waiting to be found. The challenge is the detection. These objects are cold, dark, and tiny against the immense background of space. Our telescopes are optimized for bright objects. A small, cold probe, even one actively venting gas, would be incredibly difficult to detect unless it passed very close to Earth or the Sunday. And this is what makes 3I Atlas so significant. It did pass close. It entered the inner solar system where we could observe it, and once we looked closely, we found the anomalies, the hints that it is not what it appears to be. The vast number of rogue planets, estimated to be potentially in the billions, suggests the galaxy could be full of artifacts. Ancient probes, dormant machines, all invisible to us until they happen to pass close enough to be detected. This shifts our entire framework for the search for extraterrestrial intelligence. What if intelligence prefers to remain hidden, to observe quietly, to drift through the cosmos as a silent witness? If that is the case, 3I Atlas may be the first of many, and to distinguish between the natural and the artificial, we must dig deeper into the chemistry, searching for the clearest signatures of design, exotic isotopes, and the precise ratios of the elements. To distinguish a natural celestial body from an ancient machine, we must utilize the subtle, complex language of atoms. Turning to Part 12, Exotic Isotopes and Cosmic Ray Chemistry. This field, known as cosmochemistry, analyzes the isotopic composition of cosmic materials, the ratios of atoms with the same number of protons but different numbers of neutrons. The ratios of these isotopes tell a crucial story about the origin and evolution of the material. For instance, a high deuterium to hydrogen ratio in water vapor indicates the comet formed in a very cold environment. Unusual nitrogen isotopes might suggest nuclear processing or cosmic ray exposure. These ratios are the fingerprints of history. In early 2025, a team analyzing cosmic dust particles reported something unexpected. They detected heavy isotopes in cosmic dust, specifically elevated ratios of carbon-13 to carbon-12 and oxygen-18 to oxygen-16. These enrichments were in a population of dust grains consistent with a cometary origin. The standard natural explanation is once again cosmic ray exposure. When high-energy particles bombard ice or rock, they cause nuclear reactions, creating new isotopes over millions of years. This process can significantly alter the surface composition. However, the isotopic ratios in these dust grains did not perfectly match the predictions from the standard cosmic ray models. The enrichment in certain isotopes was either too high or the pattern was subtly wrong. This led some researchers to propose that the grains experienced more than just bombardment. They underwent some form of thermal or chemical processing that further altered their composition. This connects directly to 3I Atlas. Remember the high carbon dioxide enrichment? The scientific paper we discussed attributed this to galactic cosmic rays, converting carbon monoxide ice to carbon dioxide over eons in interstellar space or the distant Oort cloud. But if the isotopic anomalies in cometary dust suggest additional, non-natural processing, then maybe 3I Atlas is not just naturally irradiated ice. Maybe there has been deliberate isotopic engineering, a selection or concentration of specific isotopes for functional purposes within the probe's design. Why would anyone engineer isotopes? There are several reasons. For power generation, certain isotopes, like plutonium-238, are ideal for long-lived power sources because of their specific decay heat. For structural materials, some isotopes have better neutron absorption properties, making them useful for radiation shielding. For propulsion, isotopic composition affects the efficiency of certain reaction processes. If 3I Atlas is a probe using radioisotope power, its internal components might be enriched in specific heavy isotopes. If those isotopes are somehow leaking into the coma, either through outgassing or ablation of surface materials, we might be able to detect them spectroscopically. The challenge, as always, is the sensitivity of remote spectroscopy. The signals from trace elements or rare isotopes are weak, often buried in the background noise of the universe. We need incredibly high-resolution instruments and long integration times. This highlights the critical need for a future mission. If we could send a probe to rendezvous with 3I Atlas, if we could collect samples of the coma dust and bring them back to Earth, we could measure these isotopic ratios with precision. We could look for patterns that suggest engineering rather than natural processes. There is also the angle of organic chemistry. Cosmic ray processing creates complex organic molecules like amino acids and sugars. However, the organic chemistry in 3I Atlas's coma is unusual. The low carbon chain abundance and the specific pattern of emissions suggests selective chemistry. This could be natural, but it could also be engineered. Imagine a probe with internal reservoirs of different volatiles, each one isotopically tailored for a specific function. Carbon dioxide, enriched in carbon-13 for thermal management. Methane with specific isotopes for propulsion. The coma composition we observe would be a controlled blend, producing isotopic signatures that simply do not match any natural comet. While this is highly speculative and direct evidence of isotopic engineering is currently lacking, the possibility exists. The broader point is that isotopes are a language. They speak of origins and processes. If we learn to read that language well enough, we might be able to definitively distinguish between a comet formed in the primordial nebula and a probe assembled by intelligent design. To take the next step, we must move beyond chemical fingerprints and find a way to resolve the object's physical form with extraordinary clarity through ultra-long baseline interferometry. Our pursuit of physical proof demands technologies that surpass the limitations of single mirrors, leading us to examine Part 13, ultra-long baseline interferometry breakthroughs and hidden microstructures. Every single telescope is bound by a fundamental physical law called the diffraction limit. This constraint means that light waves, even when focused by the largest mirrors, always create a fuzzy spot rather than a perfect point. The size of that fuzzy spot determines the smallest detail we can resolve. For an object as small as a comet nucleus and as distant as 3I Atlas, the diffraction limit of a standard telescope is nowhere near enough to see structure. We see a blob, perhaps some smearing from the coma, but no detail. We cannot resolve the difference between a natural rubble pile and a metallic framework. The only way to beat the diffraction limit is through interferometry. Instead of using one telescope, you use multiple telescopes separated by very large distances, combining their light to simulate a much larger instrument. The resolution is determined not by the size of the individual mirrors, but by the distance between them, the baseline. This technique has been perfected in radio astronomy. For instance, the Event Horizon Telescope collaboration linked radio telescopes around the entire planet, achieving a baseline the size of the Earth. This allowed them to image the structure around a black hole millions of light years away with a resolution of about 20 microarc seconds. While optical interferometry is technologically more challenging because of the shorter wavelengths of light, the technology is advancing rapidly. Facilities like the Very Large Telescope Interferometer in Chile routinely combine light to resolve surface details on distant stars and measure the sizes of asteroids. In the years 2024 and 2025, significant breakthroughs have been achieved in this field. New adaptive optics systems to correct for atmospheric distortion, better beam combiners to link multiple telescopes, and new algorithms to reconstruct images with higher fidelity. Imagine pointing such a powerful system at 3I Atlas. By combining the light from multiple large telescopes, achieving effective baselines of hundreds of meters or even kilometers, we could resolve the nucleus directly. It would no longer be a point of light, but a resolved object with discernible shape and structure. What would we be looking for? In a natural comet, we expect a chaotic shape, something like a peanut or a potato, heavily cratered, with jets emerging from random, localized active regions. There would be no obvious organization. In an engineered object, we might see subtle but distinct regularities. Symmetry is key, not perfect, obvious symmetry, but subtle, repeating patterns, alignments, or surface panels with different reflectivity or texture. We might see vents arranged in geometric patterns, perhaps equally spaced around the equator or aligned precisely with the rotation axis. We might even resolve evidence of layering an outer shell distinct from an inner core. The fixed dark lane would be particularly fascinating to image directly. If it is a shadow cast by some internal structure, high-resolution imaging would reveal what is casting that shadow. If it is a surface feature, a panel, or a crevasse, we would see its precise orientation. Either way, resolving it directly would answer many of our questions. Furthermore, we could use time-resolved interferometry. We could watch the object's structure change as it rotates. If the jets are truly fixed in space, despite the object's rotation, interferometry would show exactly how they are arranged. We could determine if they are coming from a single location or multiple locations, and whether their orientation changes in a way that suggests active control. The challenge is real. 3I Atlas is faint and moving quickly. Interferometry requires long integration times, and the object is constantly shifting its position against the background stars. But this is within the capabilities of current technology and specialized tracking systems. If the scientific community agrees that 3I Atlas is worth this extraordinary effort, these observations could be scheduled. The broader point is that our observational capabilities are finally catching up to our curiosity. We can now look for details that might reveal the difference between a natural process and intelligent design. If 3i Atlas is what some suspect, these techniques could give us the proof, but observation alone is not enough. We must also acknowledge that the technology for such a probe is not science fiction. We are, in fact, developing it ourselves right now, in the form of autonomous self-reconfiguring spacecraft. To truly grasp the long-term feasibility of the 3i Atlas probe hypothesis, we must look at emerging technologies that mirror the necessary survival traits. Examining Part 14. Autonomous self-reconfiguring spacecraft. This demonstrates that the engineering required for an eons-long machine is not futuristic fantasy, but current research. In 2025, a research team from the Massachusetts Institute of Technology, or MIT, and the European Space Agency, or ESA, published a paper describing a prototype called a Modular Autonomous Reconfigurable Spacecraft, or MARS. This is a significant breakthrough in spacecraft design. The concept is simple but profound. Instead of a single, rigid spacecraft, the machine is built from multiple modules that can detach, move, and reconnect. Each module is self-contained with its own power, sensors, and a simple artificial intelligence that controls its behavior. The modules coordinate wirelessly to adapt to changing conditions. This modularity provides extraordinary resilience. If a module is damaged by a micrometeoroid impact, the others can detect the failure and reroute functions around it. If the spacecraft needs to change its orientation, the modules can rearrange themselves to shift the center of mass. If a solar panel degrades, the system can reconfigure to better utilize the remaining power. It is a system designed for long-term autonomous operation. This kind of system is exactly what you would need for a long-lived probe designed to survive for millions of years. Think about the enormous challenges of geological timescales. Materials degrade, electronics fail, cosmic rays cause errors in computer memory. Everything breaks down. But if your probe is modular and can repair itself by rearranging components, isolating failures, and routing around them, it can survive far longer than any single monolithic structure. Damaged modules can be discarded or used as spare parts. Critical functions can be migrated to the healthiest modules. The probe is not immortal, but it is incredibly long-lived, designed to degrade gracefully rather than fail catastrophically. Now, couple this with robust artificial intelligence, not a complex, thinking entity, but simple, highly reliable control algorithms that can make basic decisions based on sensor input. These systems can maintain thermal stability, adjust the controlled venting for thrust, and monitor radiation levels. Modern spacecraft artificial intelligence can already handle these tasks, and future systems will be far more capable. An AI-equipped probe could navigate autonomously, adjusting its trajectory to avoid hazards or target regions of interest. It could go dormant as it recedes from the sun and ramp up activity as it returns. Crucially, it could learn, adapting its behavior based on accumulated experience to become more efficient over eons. This is not a distant vision. This is engineering that we are developing right now in 2025. If we can build these systems with just a few centuries of technological evolution, what could a civilization with millions of years of development build? Imagine 3i Atlas as a self-reconfiguring probe. The outer layer of ice and dust is the simple camouflage and radiation shielding. Beneath it, an interconnected framework of modules handles specific functions: power, thermal control, venting, and navigation. The central artificial intelligence coordinates everything, managing the rotation and the thrust. Over millions of years, the communication systems might have failed. The original mission parameters might be corrupted, but the core functions power, stability, and venting still work, maintained by the surviving modules and the AI's optimization algorithms. This would explain the dual nature of 3I Atlas. It behaves in ways that seem controlled, yet also slightly erratic. It is not a perfectly functional machine, but a system that has been running for millions of years, patched and repaired by its own programming, degraded but not destroyed. The fixed jets and stable thrust are the signatures of a system that is still barely performing its original, engineered task. If we can build self-repairing modular spacecraft now, then a millennium from now, our descendants might send probes into the cosmos that look exactly like what we are speculating 3I Atlas might be: long-lived, autonomous, and disguised as natural objects. If that happens, then future civilizations might encounter them and ask the same questions we are asking tonight. Is it natural? Is it artificial? The final piece of the puzzle, then, is not in the object, but in our tools. How do we distinguish between the strange but natural and the genuinely engineered? We must employ our own artificial intelligence to help us recognize the subtle, hidden patterns of design. We must look to AI-driven anomaly detection. We now conclude our investigation by turning to the most modern of our tools, focusing on Part 15, AI-driven anomaly detection. This is the frontier where human assumptions fade and pure pattern recognition takes over, a technology that may finally resolve the ambiguities of 3I Atlas. In 2025, a team at Stanford University published a significant paper on exoplanet atmospheres. They had been using machine learning algorithms to analyze spectral data from the James Webb Space Telescope, searching for the chemical fingerprints of life. What the artificial intelligence found was completely unexpected. The algorithms detected repeating patterns in the spectra, subtle periodicities in the absorption lines that human astronomers had previously dismissed as background noise or instrumental errors. But the artificial intelligence relentlessly flagged them, insisting they were real signals. The team reprocessed the data and confirmed the finding. There were indeed periodic variations in the atmospheric composition of several exoplanets, cycling on timescales of days to weeks. The patterns suggested complex atmospheric dynamics, or, at the extreme limit of speculation, artificial modulation. The implication for astronomy is profound. AI can find signals in noisy data that humans miss, and some of those subtle signals may be signs of things we are not even explicitly looking for. This is immediately relevant to 3I Atlas because we have been analyzing its behavior with human eyes and human assumptions. We fit the data to what we expect to see in a comet. But what if we are missing subtle periodicities or correlations that only become apparent when you analyze thousands of spectra and astrometric data points with a machine learning algorithm? Imagine feeding all the available observational data, the spectroscopy, the polarization, the light curves from 3I Atlas, into a highly specialized artificial intelligence system designed for anomaly detection. You would train it on the spectra of hundreds of known, normal comets. establishing a precise baseline for what a natural object looks like. Then, you would give it the atlas data and simply ask, what doesn't fit? The artificial intelligence might find repeating cycles in the carbon dioxide emission that correlate with the object's 16.2-hour rotation, but not in the chaotic, smeared way you expect from a simple spin. It might detect subtle shifts in the nickel-to-iron ratio if the nickel reports are confirmed that suggest modulation or control. It might identify correlations between the timing of the symmetrical jet activity and specific chemical compositions, patterns that hint at feedback systems or deliberate regulation. These are the kinds of signals that would be invisible to human analysis, requiring days of staring at graphs, but they would be obvious to a well-trained machine learning model. If those signals are there, pointing definitively toward engineering, then AI might be the tool that finally confirms the hypothesis. There is a deeper, almost philosophical point here. As our technology advances, we are no longer limited by our instruments. We are limited only by our ability to recognize patterns. Artificial intelligence extends that ability. It allows us to search parameter spaces too vast for human minds. It lets us find needles in haystacks, structure in chaos. If 3I Atlas is artificial, the artificial intelligence will likely reveal it. Not because the artificial intelligence is smarter, but because it is objective and free from bias. It doesn't start with the assumption that comets must be natural. It simply looks at the data and says, this is different. Once we deploy this capability, once we have artificial intelligence systems routinely scanning astronomical data for these kinds of anomalies, we might begin to find many more objects, like 3I Atlas. We might discover that our solar system is full of strange things that don't quite fit the models, objects that behave in ways we can't easily explain. Some will be exotic, natural phenomena, but others might be something else entirely. This brings us to the end of our current investigation, but not to a conclusion. We have anomalies, we have a hypothesis, we have data that is highly suggestive, but not yet definitive. We have an object that looks like a comet, but behaves like something more. And we have a growing, quiet sense that maybe, just maybe, we are looking at the first evidence of an intelligence native to our own solar system. If that is true, then this is the most important discovery in human history. It means we are not alone. It means intelligence has arisen in our own cosmic backyard. But even if it is not true, even if 3I Atlas is a perfectly natural object, the investigation has forced us to think differently. It has pushed us to develop new technologies, new methods, and new ways of seeing. It has reminded us that the universe is stranger and more complex than we ever imagined. We must keep watching. We must keep analyzing. We must stay open to the possibility that the answers we seek might be closer than we think. We now confront the most profound objection to the ancient probe scenario, an enigma known to researchers as the Great Silence. If an advanced civilization, whether biological or machine, arose in the outer solar system millions of years ago, the very question that follows is simple and chilling. Where are all the others? Why is the solar system not teeming with their artifacts? This problem, originally posed to question the existence of life in the universe at large, becomes acutely focused when applied to our own cosmic neighborhood. If such a civilization existed, if they built self-replicating machines, what the great mathematician John von Neumann first described, then by the simple logic of exponential growth, we should be drowning in relics. The entire outer solar system, stretching from the edge of the Kuiper belt to the far reaches of the Oort cloud, should be full of them. And yet, we see nothing. Or do we? You must remember the humbling scale of our exploration. We have only been looking at the outer solar system with any real scrutiny for about 50 years. That is a mere fraction of a second in the vast expanse of cosmic time. The Kuiper belt alone is a volume of space so enormous that if you tried to search it systematically with our current telescopes, you would need tens of thousands of years. When we say we've explored, what we truly mean is we've glimpsed a few dozen objects in detail and catalogued maybe a few 100,000 more. We've studied maybe a few thousand Kuiper belt objects in any detail, and most of our observations are simply dots of light, reflections, or orbital parameters. That is like looking at 3 grains of sand on a beach and declaring you understand the ocean. The machine intelligence of a ghost civilization would inherently understand this challenge of detection. If they intended their probes to last for millions of years, they would design them to be invisible. Machine intelligence doesn't need organic chemistry. It just needs energy, materials, and time. They would have engineered their probes to masquerade as unremarkable chunks of ice and rock. Think about the principles of camouflage in this context. Their probes would be cold, dark, and covered in a thick layer of natural ice and dust. Our modern telescopes are primarily optimized for finding bright objects, stars, galaxies, things that emit or reflect a lot of light. A small, cold probe, even one actively venting gas, would be incredibly difficult to detect, especially at the vast distances of the outer solar system. Furthermore, the design itself could incorporate stealth features. Perhaps the structure is based on materials that absorb radio waves, or surfaces treated to scatter light in specific ways. The polarization anomaly we discussed earlier, the extremely negative polarization of 3I Atlas, suggests unusual dust particle sizes, shapes, or possibly a metallic film features that could easily be part of a subtle, long-term camouflage strategy. The only time we would ever notice such an object is when it malfunctions, or when it is forced to reveal itself by entering the inner solar system, where our detection capabilities are highest. 3I Atlas is unique, precisely because it is the rare exception, the one probe that either broke down or woke up. Its fixed shadow, its symmetrical jets, and its controlled acceleration are all signs of a failing disguise. It is a machine that, after eons of silence, has started to activate or degrade, and its systems are revealing themselves through slight imperfections. This brings us to the profound idea of patient intelligence. A sufficiently advanced machine civilization, or its autonomous descendants, would not think in human timescales. It could wait 1,000,000 years for something interesting to happen. It could drift, barely active, for eons, and conditions have changed. The inner solar system has become interesting again. After billions of years of quiet, a technological species, us, has emerged on the 3rd planet. We are leaking radio transmissions into space. We are launching spacecraft. We are testing nuclear weapons. If you were a dormant probe, built to monitor this system, this surge of activity would be the event that triggers your attention. The Great Silence, therefore, might not be an indictment of the hypothesis. It might be an artifact of our own technological youth. We are only now developing the telescopic power, the computational algorithms, and the theoretical frameworks necessary to recognize an ancient, camouflaged artifact when we see one. The other probes are still out there, dormant, disguised as asteroids or Kuiper Belt objects, waiting for the proper trigger, or simply waiting for their own internal systems to break down enough to reveal a single, subtle, unnatural anomaly. 3I Atlas is merely the first we've managed to catch in the act. The great silence is not empty, it is merely quietly populated. We must move now from the silence to the whispers of energy that fuel these ghosts. Examining the question of power and longevity, our gaze now focuses on the source of the object's incredible endurance, delving into Part 17, Power, Longevity, and the radioisotope heart. If 3I Atlas is a probe that has functioned for millions of years, its power source is the key to its survival, an engineering challenge that requires overcoming the relentless decay of time. In the cold, dark environment of the outer solar system, solar panels are virtually useless. The sun is merely a bright star. To power a machine for eons, you need a source that is long-lived, compact, and completely independent of the Sunday. The answer, even for a hypothetical alien intelligence, must rely on the fundamental physics of the universe, radioactive decay. We ourselves use this technology for deep space missions. It is called the radioisotope thermoelectric generator, or RTG. This device converts the heat generated by the natural radioactive decay of long-lived isotopes, such as plutonium-238 or americium-241, directly into electricity. This process can provide stable, low-level power for centuries. Voyager is still transmitting data after decades, powered by this very concept. Scale this up with more efficient systems or more advanced isotopes, and you can power a probe for millions of years. You don't need a fusion reactor. A few kilograms of plutonium-238, properly configured, could generate the necessary heat and electricity to sustain computational systems and maintain structural integrity. The ability of rogue planets to maintain internal heat through radioactive decay reinforces this idea. Objects can exist in the cold darkness while maintaining internal energy. An ancient intelligence would have likely engineered its power system using a high degree of redundancy. The probe's core would contain multiple, shielded RTGs, ensuring that if one generator failed, others could take over. This central heat source is also vital for the object's thermal management, preventing critical internal components from freezing solid at temperatures near 50 Kelvin. The need for long-lived power also circles back to the anomalies we observe in the Comet. If the object utilizes controlled venting or thrusting to adjust its trajectory, it requires a steady supply of energy to run the gimbaled thrusters, the valves, and the central control system. This energy consumption, while small, is sustained. Furthermore, the required thrust is small, around 0.02 millimeters per second squared. This is exactly the kind of low, continuous thrust that RTG-powered systems or advanced ion engines utilizing radioisotope power are designed to generate over vast periods. The smooth, directional, and persistent acceleration of 3I Atlas fits this power profile disturbingly well. This focus on power leads us to a fascinating thought experiment: the engineering of immortality. An engineer building a probe for millions of years wouldn't focus on performance. They would focus on longevity. They would use materials and designs that are simple, mechanical, and resistant to degradation. The probe would be designed to degrade gracefully. Over time, some electronic components might fail, and some RTGs might diminish, but the core systems, the propulsion and stabilization, would be maintained at a minimal level by the surviving units and the probe's own self-repairing programming. This relentless need for energy efficiency could also explain the compositional oddities. The high carbon dioxide enrichment in the coma, which is unusual for a natural comet, could be a deliberate choice for propellant or thermal management, because carbon dioxide is easily stored and provides efficient thrust through controlled sublimation. The probe is not venting random ice. It is venting a tailored volatile for maximum long-term efficiency. The radioisotope heart of 3I Atlas, though unseen, provides the logic that connects its strange behavior to intentionality. It is the engine that allows the probe to be both a natural-looking comet, the ice shell, and a long-lived machine, the internal power. But even with all this advanced engineering, the question remains: what happened to the core message? Why is it only waking up now? This leads us to the mystery of the dormancy protocols. Having established the immense longevity provided by the radioisotope heart, we now must address the object's temporal behavior, exploring Part 18, dormancy protocols, and the activation trigger. If this object was built to last for millions of years, it would have spent the vast majority of that time in a state of minimal activity, a deep, frozen sleep. A machine designed for eons must conserve its limited energy and resources. In the outer solar system, where temperatures are near absolute zero, the probe would enter a dormancy protocol, minimizing power consumption, shutting down non-essential systems, and relying solely on the RTGs for basic monitoring and survival heat. It would be a state of suspended animation, waiting patiently for the conditions to change. This concept aligns with the idea of patient intelligence, a mind that thinks in geological timescales. The probe is designed to wait 1 million years for something interesting to happen. The critical question, then, is: what broke the silence? What event, after eons of quiet drifting, triggered the probe to activate its higher-level systems, begin active thrusting, and start displaying the anomalies we now observe? The hypothesis is that the probe was programmed to detect one specific thing: the emergence of technological intelligence in the inner solar system. This trigger would likely be a set of thresholds, not just a single event, but a sustained pattern of activity that signals the rise of a new technological species. Possible triggers could include radio emissions, the steady leakage of powerful radio signals into space, which we have been producing in volume since the mid-1900s, technological signatures, the detection of nuclear detonations, or the launch of high-velocity spacecraft beyond Earth orbit. Atmospheric changes, subtle, detectable alterations to the Earth's atmosphere caused by large-scale industry or technology. When the probe's sensors, which might be degraded but still functioning, cross this threshold, the activation sequence would begin. It would wake up from its frozen sleep. The core AI would execute its primary objective: trajectory correction. It would use its controlled venting to abandon its stable outer solar system orbit and adjust its course to ensure a close flyby of the inner planets, specifically Earth. This scenario provides a chilling explanation for the very act of its discovery. 3. I-Atlas was discovered in 2024, entering the inner solar system during an era when humanity is more technologically active than ever before. We are launching satellites, broadcasting radar, and exploring the cosmos. It suggests we are not discovering the probe by accident. It is discovering us. It is responding to our presence, to our technology, to the fact that we have finally become noticeable. However, the probe is not functioning perfectly. The fixed shadow, the subtle non-gravitational acceleration, and the chemical anomalies are all signs of a machine that is malfunctioning after eons. It is capable of the basic, low-level functions required for self-management, thrust, and venting, but the complex task of communication may be corrupted or lost entirely. It is a machine trying to carry out an ancient command, but its systems are crumbling. The erratic control we observe is the result of a primitive AI trying to optimize a failing system. It's like a complex clock that still tells time, but has lost the mechanism to chime on the hour, revealing the internal mechanics through its quiet struggles. The probe might not be designed to communicate with us at all. It might be designed to simply observe and record, transmitting data to a distant receiver that may have long since been destroyed. It is a silent observer, carrying out a mission that predates our species. The dormancy protocol, therefore, was successful for millions of years, but the activation sequence, triggered by the dawn of human technology, has resulted in a machine that is visible to us only because of its degradation. This realization forces us to consider the fate of its builders. What happened to the civilization that built a machine so patient? We must now turn to the hypothesis of the precursor civilization's demise. We now turn our attention from the machine to its creators, contemplating the mystery of Part 19, the precursor civilization's demise. If 3i Atlas was built here, the question of who built it is inseparable from the question of why they are no longer here. The most straightforward, and perhaps most common, answer is a civilization that simply no longer exists. Something that arose in the outer solar system billions of years ago, perhaps during a brief window when conditions were slightly more favorable, and then vanished, leaving only their machines behind as a final legacy. This aligns perfectly with the model of the time capsule. If you are a civilization that knows its end is imminent, your final, most enduring act would be to build something that will outlast you. You create autonomous systems, probes, and repositories of knowledge encoded in durable materials, designed to survive until another intelligence finds it. 3i Atlas could be exactly that, a message in a bottle drifting through the solar system for eons, waiting for someone like us to notice. But why would such an advanced civilization die? We can only speculate on the causes of a cosmic-scale demise. Perhaps it was a natural catastrophe in the outer solar system, a massive bombardment event, or a shift in the gravitational dynamics of the region. Perhaps it was a more subtle, internal failure, a civilization that evolves to be entirely mechanical or dependent on machine intelligence might simply have achieved a state of terminal stability, losing the drive for evolution and simply fading away. The demise could also have been intentional. Maybe the builders foresaw a catastrophic event, such as a large stellar event, or even the eventual death of their homeworld, and engineered the probe as a means of preservation, transferring their knowledge, or perhaps even their consciousness, into the durable, mechanical shell of the Atlas probe. Consider the alternative hypothesis that the probe is biological in origin, but not in a way we recognize. Life might have evolved in the subsurface oceans of distant moons, like Europa or Enceladus, eventually developing technology and expanding outward. This life, adapted to high pressure and cold chemistry, would be completely independent of the sun, and their technology would reflect this origin. If their homeworld became uninhabitable, these outer system denizens would launch probes like Atlas as a final act of dispersal and monitoring. Then there is the strangest, most unsettling possibility of all, that the builders are still out there. They reside in the darkness beyond Neptune, watching us as we discover their creation, but they have simply shown no interest in making contact. Perhaps they are observing a prime directive, waiting to see what we do with our fledgling technology before revealing themselves. Perhaps they consider us too primitive or too dangerous and prefer to maintain the great silence. If this were true, it would mean that we, the dominant technological species on Earth, are living alongside an ancient, superior intelligence that has simply chosen to ignore us. The only reason we know they exist is because one of their machines, designed to be invisible, malfunctioned in a way that produced a geometrically perfect shadow. Whether the civilization is gone, a ghost ship sailing through the void, or merely hiding, the imperative of the probe remains the same. It is carrying secrets we are only beginning to uncover. The journey to understand it requires that we look beyond our own conventional assumptions about what a civilization should look like and how it must behave. We must look at the future of our own technology and see how our emerging abilities might mirror the ancient design of 3i Atlas. We arrive now at the final reflection, exploring part 20, the human reflection and the call to rendezvous. As we look at 3i Atlas, we are forced to see not just an ancient alien artifact, but a mirror reflecting the destiny of our own burgeoning spacefaring species. If we can build autonomous self-reconfiguring spacecraft in the year 2025 machines, designed to repair themselves, adapt, and operate with basic artificial intelligence, then it is logical to assume that a civilization with millions of years of development would have perfected this concept. Our own emerging technology provides the plausibility analog for the Atlas probe. Our future probes, launched a century or a millennium from now, will be long-lived, autonomous, and disguised as natural objects designed to explore the galaxy and survive for geological timescales. If, centuries from now, other civilizations encounter them, they will ask the same questions we are asking tonight. Is it natural? Is it artificial? Who built it? This realization suggests that 3i Atlas is not an inexplicable miracle. It is a universal stage of technological evolution. It is the logical conclusion of building a machine designed for maximum longevity in the cold vacuum of space. The anomalies, we see the fixed jets, the stable rotation, are not magical. They are simply good engineering applied over an immense period of time. This cosmic puzzle forces us to change our approach to the search for extraterrestrial intelligence. We've been listening for loud radio signals, or looking for massive structures around distant stars. But what if the greatest evidence of intelligence is quiet, camouflaged, and close to home? What if the sign of advanced civilization is the ability to hide? The anomalies of 3I Atlas push us into a new era of scientific inquiry, where we are developing new tools, specifically to detect the unexpected. We are training artificial intelligence algorithms to scan astronomical data, not just for biosignatures, but for anomalies patterns that don't fit the natural model, correlations that hint at engineering, or structure in chaos. If the probe is artificial, our AI will likely be the tool that finally reveals it, because the machine is objective and free from the human bias that assumes comets must be natural. This leaves us with one critical, immediate conclusion. We cannot solve this mystery from Earth. We cannot penetrate the disguise of 3I Atlas with remote spectroscopy and interferometry alone. The only way to definitively answer whether it is a geological fluke or a ghost from our past is to go there. The only path forward is the call to rendezvous. We need to launch a mission to intercept 3I Atlas, a probe equipped with high-resolution cameras, mass spectrometers, and isotopic analysis tools. If we could collect samples of the Comet dust, we could measure isotopic ratios with far greater precision, looking for the telltale signs of engineered materials like plutonium-238 or non-natural nickel enrichment. If this object is what some suspect, if it is truly artificial, then it represents the most important discovery in human history. It means we are not alone. It means intelligence has arisen in our own cosmic backyard, not once, but at least twice. Even if 3I Atlas turns out to be a natural object with unusual but ultimately explainable properties, the investigation has already been worth it. It has forced us to develop new technologies, new methods, and new ways of thinking about the cosmos. It has prepared us for the possibility that the universe might surprise us, that the answers we seek might be much closer than we think. We keep watching, we keep analyzing, we push for the mission, because out there in the darkness, spinning through the void, wrapped in ice and shadow, there is an object that refuses to be ordinary, and whether it is a comet or something more, it is challenging us, daring us to look closer. And so, we leave 3I Atlas to its silent, 60n.2-hour rotation, wrapped in ice and the shadow of possibility. We have journeyed from the fixed dark lane to the promise of artificial intelligence, seeking to decipher the language of an object that refuses to be ordinary. The human journey is defined by this curiosity, by the impulse to look closer at what the universe sends us, even when it challenges our deepest assumptions. We have much to learn, and our species is resilient. Our ancestors survived soup that might kill you, so we can survive a good cosmic mystery. History bends, but never breaks its commitment to wonder. Sleep well, and let the questions drift with you into the dark.